Well guys, this is the last one of our series of transformations ones, apart from the next video which will be using matrices, but just using the conventional functional based ones. This is the last one. It's combinations of transformations going backwards, and I've got some super good stuff in store for you. So let's make a start. Okay, calculations using the recommended logical method. That's my recommended logical method, going backwards. Okay, all of this video is for going backwards. The previous video was going forwards. Okay, so let's have a look what we've got for you. Name a sequence of transformations that transforms the function f of x equals 1 over x into the function g of x equals 3 over x minus 5 plus 4. Okay, so this is the backwards technique. We have to come up with the sequences of steps or transformations required to get from f of x to g of x. Now, and we have to sketch g of x, stating the equations of any asymptotes and the coordinates of all the axes, intercepts. Well, that's going to be pretty easy. The first part is really what we're needing to be concentrating on, but it's usually, this can be the context of the kind of question that they will ask you, hence the part B there, alright? Part A, okay, so we've got the original equation there, y equals 1 over x, and we've got the transformed equation, y equals 3 over x dash minus 5 plus 4. Now what we've got to do, guys, is we've got to get these orphan terms belonging to an x or a y. That guy's just floating out in mathematical cyberspace, and he's got to belong to the x or the y. It's easier to make him belong to the y than the x. This guy here is also, that's no good because the original form of the equation was 1 over something, so that 3 over something's no good. And it's actually easier to make him belong to the y as well, as I'll show you, and that's what we do to get them in equivalent form. So, put equation 2 into equivalent form so that all the extra terms, that's the 3 and the 4 and the 5, they need to be specifically attached to either an x or a y, and so the original form of the original equation on the right hand side is preserved or maintained. The minus 5 belongs to the x, no doubt, that does, but these guys are a bit dodgy. They don't belong really anywhere to an x or a y term specifically. So that's the way I've rearranged it, right? So I've basically subtracted 4 from both sides and divided both sides by 3 to get that. Now it's very obvious now that all those extra terms are belonging to x's or y's. So equating equivalent terms, we get this: y dash minus 4 over 3 is the same as the original y up here, and x dash minus 5 is the same as the original x up there. Yes, all good. Now, because we're going backwards, we have to solve these for y dashed and x dashed. So that's the y dashed and x dashed equations. Does that look right? Yes, it does. And what we're going to do now is we can just state the transformations that were happening here. So I'll just do it for you, and then we'll just unfold all the steps that I've put for you on the video presentation. So what looks like to me like y has got to be multiplied by 3, so that's a dilation of a factor of 3 from the x-axis, and then we're translating upwards by 4 units, and this guy here, he's being translated by 5 units to the right. That's the way I get it. So yes, that's right, and so that's a dilation of a factor of 3 from the x, like I said, translation of 4 units up, and a translation of 5 units to the right. And Bob's your uncle, and it's looking great. Now, we're going to sketch the graph now, stating the equations of any asymptotes, part B, and the coordinates of all the axes, intercepts. Now, we already know how to do all this. What have I written there? Put equation 2 into equivalent form. Oh, that's just where we got to before. But however, oh yes, before we do part B, there's something very interesting here. Very interesting, and that is, alternatively, I was fiddling with this, and I came up with this amazing revelation, which I'm going to share with you. Instead of basically making that 3 belong to the y, like I did before, I had y dash minus 4 over 3. I could actually put that as a 1 over 3. I could put it as x dash minus 5 over 3. I could, like that. And that means that I've put that 3 now belonging to the x term, because it's definitely belonging to the x because it's dividing the x dash by 3. Yes? Now that's very interesting, and that's going to get me a different sequence of transformations. You watch. So equating equivalent terms now, we get a y dash minus 4 equals y, not y dash minus 4 over 3 equals y. We get x dash minus 5 over 3 equals x. Now, if we solve that for x dash and y dash, we get that. Does it look right? It does. Now, if I rattle off that sequence of transformations, ladies and gentlemen, I will get this, a dilation of a factor of 3 from the y-axis. That's this 3 here, right? And then I'll get a translation of 5 units to the right. That's that one there. And this one here will be a translation of 4 units up. There it is. Now, that's different from what we got before. What we had before was that. Now I thought, oh, well, what I thought was, oh, yes, well, that will lead to the same, end result. That'll change points, a given point on the original graph of y equals 1 over x to the same point. It just must be a different way of getting there. However, it's not actually true. They actually transform to different points. That is the amazing thing. And I'll show you something. It actually taught me something doing this video, so I'm going to share it with you. When you think about these things deeply, the most amazing revelations come up and you understand them so much better. So, let's have a look. These are different, but they're both correct. Confusing? Definitely. See over. Here we go. So that's where we got to. They're both different steps, transformation recipes, but they're both correct. So, it sounds confusing, but here's why. Okay, now, I tried this out. I said, all right, look, if I take a point 1 and 1 on the graph of y equals 1 over x, which it is on that graph, when x is 1, y is 1, and then I basically use that recipe, the first recipe, to see where that point would end up. Where would it transform to? You know, like on a point-by-point basis, but picking point x is 1, y is 1. So I said, okay, according to this, basically, the first set of transformations, x is 1. Therefore, x dashed is 3x plus 5, which would get me to 8, wouldn't it? And y was 1. And using the recipe for the transformations, y dash would be 1 plus 4, which would get me 5. So in other words, 1, 1 goes up to 8 and 5. Now, ladies and gentlemen, according to the second set of transformations, if x is 1, x dash would be x plus 5, which would be 6. And if y was 1, y dash would be, what is it? 3 plus 4, which is 7. Now, what was it again? Y, yeah, factor of, yes, that's right, factor of 3 from the x-axis plus 4. That's right, it equals 7. So, yes, so basically what we're saying is there that goes to, the y dash goes to 7. So we're saying 1 and 1 goes to 6 and 7. So that seems completely weird because up here we've got 1 and 1 going to 8 and 5, 1 and 1 going to 6 and 7. So how can this be? How can this be? Something seems wrong because 1 and 1, x and y, x is 1, y is 1 maps to different points. However, testing these 2 points, I decided, well, I'll see whether 8 and 5 is a valid point on the transformed curve, and I'll see whether 6 and 7 is a valid point on the transformed curve. And it's actually, when you plug in x as 8, you get y as 5, and when you plug x as 6 in, you get y as 7. So that really makes you feel, what's going on here? But actually, it's completely logical. They're both valid points on the transformed function. What's going on here is similar to what went on in the first video when I basically, on transformations, the dilations one, when I considered the graph of y equals x going to the graph of y equals 2x. And I showed you in that video that if you took the point 1 and 1, x is 1, y is 1, you could basically consider 1 and 1 morphing up vertically by a dilation of a factor of 2 from the x-axis to 1, x is 1 and y is 2, or you could do a horizontal dilation from x is 1 and y is 1 to x was a half, y is 1. So in other words, you can get point 1, 1 in brackets, x is 1, y is 1, transforming to completely different points, and still, if you consider all those points collectively, all transforming either upwards or horizontally across inwards towards the y-axis, as in that example, you will still end up with the same function. You will still end up with the same transformed function. That's what's going on here. So this means that under the two different sequences of transformations, individual points map to different locations on the transformed curve, but collectively they all map in a way that the same transformed curve is created. Isn't that amazing? It is amazing to me. Now, where are we getting to with all this? Yes, this is B now. B. So we have a dilation of a factor of 3 from the x-axis. We've got this is where we got to. I'm taking the first sequences of transformations, right, that I got on the previous screen. Translation of 4 units up and a translation of 5 units to the right. Now here we go with all this palaver. The intercepts, if we're sketching graphs, we have to do that. Y-intercept means x is 0. Solving for that, we get that, and therefore we get a y-intercept of 17/5. The x-intercept where y equals 0. Solving for that situation, we get basically x is that. So there's our x and y intercept, right? Now we're going to use our translation recipe here to work out what we think is going to happen to this graph of 1 over x to get to that thing. So it looks like we've got a dilation. Well, we won't worry so much about the dilation, but the translation of 4 units up means that we're going to have a horizontal asymptote where y equals 4. Now, instead of the x-axis being the asymptote, and we're going to have a translation of 5 units to the right, so we're going to have an x equals 5 asymptote instead of the y-axis. So let's draw that. There it goes. There we go. There it goes. Now, we can sketch our graph in. There it is. And we can put our intercepts in because we just worked them out. There they are. There they are. And there's our graph labelled, and everything's beautiful. We're in maths heaven again. Thank you. Thank you. So here we go to sketch this thing now. We'll use the same technique. We'll use our transformations to work out what we think's happened to the base model graph of y equals root x to get to that thing. So if we've got y equals root x as an original starting point and we go with that, we've got to put them in equivalent form, and that would mean getting rid of that 4 from the right hand side and the -1 outside the square root sign, because that -1 doesn't belong to the x term because the x is trapped inside the square root term. So this is what we do. The right hand side form of the equation has to be preserved, so that's what you do to it. You add 4 to both sides and then multiply both sides by -1 and you'll get that. Okay, now that's in equivalent form now. So equating equivalent terms, we've got minus in brackets y dash plus 4 equals y, and we've got x minus 5, x dash minus 5 equals x. Now we're going backwards, so we have to solve for y dash and x dashed. That's it. Now you can just rattle off the transformations. So you look at it and see whether you think what I'm about to say is right. Right, a reflection about the x-axis. That's what's creating this, that thing, that minus, because y is going to minus y. We've also got a translation of 4 units down, which is this beastie, and we've got translation of 5 units to the right. That's good. That's good. Now, I suppose we have to go and get all this. Oh no, there's no intercepts, are there? There's none. So does this make sense? Reflection about the x-axis. So the original function was going up here, like this kind of thing. So basically then you reflect that about the x-axis, kind of brings it down here, kind of thing. Then we're moving it 4 units down and 5 units to the right, which gets us that. That's right. 5 units to the right, x is 5. 4 units down, y is minus 4, where this point here was originally on the origin. That's great, isn't it? It works. Now we've got to sketch this truncus. Okay, we'll compare that to a base model truncus, which would be y equals 1 over x squared. And then we'll work out what the transformations were. Equivalent form needed. So I'd suggest y dash minus 1 over 2 would be the best, easiest way to get that 1 and that 2 belonging to either an x or a y, in this case a y term. If we put them into equivalent form so that all the extra terms are attached to either x or y, so that the original form of the right hand side of the equation is maintained, we do what I just said. Y minus 1 over 2 equals that. Now we can do the equating equivalent terms. We get that, don't we? Oh, I think we do. And we get the x dash minus 3 is the same as the x. Yes, it is. If you compare equation 2a to 1, you'll get that. Now we've got to solve it for, we're going backwards, so we've got to solve it for y dash and x dash, and we can just rattle it off, guys. It looks to me like we've got a dilation of a factor of 2 from the x-axis, a translation of 1 unit up, and a translation of 3 units across, compared to the original truncus. So that would make sense. I suppose we'd better do the, yes, that's right, dilation factor of 2 from the x-axis, translation of 1 unit up, translation of 3 units to the right. I suppose we better work out the intercepts. Well, that's very boring, but you know, you have to do it if you're sketching a graph. So the y-intercept occurs when x is 0, so let's work that out. That looks like 11 over 9, so our y-intercept is 0 and 11 over 9 coordinates. When the x-intercept occurs, y equals 0, so therefore we're going to solve that situation. And, oh no, that's got no solution, because that's a squared term equaling a negative. That can't happen, so there's no solution, so there's no x-intercept. And I think that probably makes sense if you look at this, because you've got a, yeah, it's moving 1 unit up, so it doesn't go anywhere near the x-axis, because the original truncus is sitting above the x-axis anyway. That makes sense, so no solution. So let's go. Here we go. Now, what are we doing? We're moving 3 units to the right and 1 unit up, so there are our new asymptotes. And there's our, oh, look at that, it's beautiful. There's our y-intercept. Yeah, it's really lovely, isn't it? So we're doing fine. We're doing mighty fine. Yeah? Now what's this? State the sequence of oh, here we go. Now we're going from the complicated, this is the original, which is the complicated one, into the base model. Now, we're still doing my logical technique here, but you wait till we get to the learned quick technique, and you see what I have to do to make this work for the Dr. T quick learn technique going backwards. It's a bit of a mess, really. Anyway, let's go with but we're still doing the logical Wolfie technique here, the preferred one for me anyway. So that's the original, that's the transformed, right? We have to still put them in equivalent form. So I think, why not go y minus 5 in brackets with a minus and divided by 2. That would be very equivalent, like this. Yeah, that's right. Now, we can equate equivalent terms, yes. So y dashed is minus, is that right? Yes. That's right, minus, in brackets, y minus 5 over 2. X dashed is x plus 3. And solving it for y dashed and x dashed, we have that. Don't we? Hence we have, now we can rattle them off, guys, we can rattle them off. You think about it before I say it. What have we got here, and what have we got here? Right? What have we got? We've got basically the lot here. We've got a dilation of a factor of half from the x-axis. That's where we're getting this half, because the y is being compressed into half its normal height. We've got a reflection about the x-axis, which is where this minus thing is happening, because the y is going into minus y. And we're also translating by a factor of 5 over 2 up. And we've got a translation of 3 units to the right. Okay? That's what we're doing to the original 1 over x graph. Right? We're doing everything to it. We certainly are. So we don't have to sketch the graph, thank goodness. We're just doing the sequence of transformations. So that looks like it. Yes, NB. If the, oh yes, this is a very interesting twist, guys. I just played with this a little bit. Look, if we had basically said, look, y dash is equal to this, right, like I got there, but I didn't basically get rid of that bracket. If I just left it like that, how would you then state the sequence of transformations? You'd have to be very jolly careful, I'm telling you, you would. But this is what you do. This is what you do. You could have expressed that thing with the brackets in it, like down this thing, with the brackets in it as this. You have to do the bracket first. So you'd say, well, it's a translation of 5 units to the left. That's what's inside the bracket. No, not... What? It's a translation of... Wait a minute, I'm going to fix that up. Just a minute. I mean a translation of 5 units down. I had a translation of 5 units to the left, so pardon my dyslexia. We're changing the y, so that's in what's in the bracket is a translation of 5 units down. Now, Now you can do the rest of it. We better do the minus. That means a reflection about the x-axis. And this means, well, probably we'll do the dilation first. That's a dilation of factor of 2 from the x, and then a reflection about the x. Is that right? I think that's right. So brackets first, a dilation of factor of half from the x. No, I'm sorry, that's supposed to be, yes, that's supposed to be a dilation of a factor of a half from the x. I think I said 2. Now that's where I'm getting myself all mucked up and starting to use the Dr. T technique. So that's why you've got to be so careful. It's happening to me now. So, you know, this is the actual transformations I'm reading. So if you see a half, it means a half, right? Because it's logical, that's why. So, yes, right? So that's basically a dilation of a factor of half in the y directional from the x-axis, and then the last bit is the reflection. That's a y reflection, therefore it's about the x-axis, right? Yes, that's right. Now, that's the equivalent way, but you'll see that I had to do them so that the bracket thing was first if I left the brackets in. Now, you might, look, I would recommend that you don't leave brackets in. Just multiply it all out like this and then just rattle them off one after the other. It's much more, it's safer, I think. It's much safer. But I just thought I'd play with it and show you what you do, just in case you were wondering. And you couldn't ask me because this is a video. Okay, etc. Now, calculations using the learned or quick technique. Here we go. Now, we're doing backwards in this video. Name a sequence of transformations that transforms the function f of x equals 1 over x into g of x equals 3 over x minus 5 plus 4, and then sketch the graph. Well, if you don't mind, I won't sketch the graph again because I've already sketched it, but I'll do the first bit for you using the quick cookbook technique. The learned rules are there, so therefore we start off with the original. That's the transformed one. Putting them in equivalent form, we have to say y minus 4 over 3 that's the best way. Y dash minus 4 over 3 is 1 over x dash minus 5, and from the learned rules we have to name the transformations which take place from 1 to get to 2a in D to R to T or Dr. T order. Dilations, reflections, translations. So can you see any dilations anywhere? Now remember, this is the Dr. T technique, so everything's backwards. So this means a dilation of a factor of 3 from the x-axis. That's right. That's the dilation. There's no reflections. There's 2 translations. 4 units up and 5 units to the right. Yes, that's right. So dilation of 3 from the x-axis. That's right. Translation 4 units up and 5 units to the right. That's right. That was pretty easy, wasn't it? That's why people like Dr. T. Now, sketch the graph of that. Yes, same old, same old. We use the transformations as a guide to what the graph's going to look like. We use the base model as our starting point. Y equals root x. And that's our transformed version with the dashes on it. Put them in equivalent form, and so that the right hand side of the equation is preserved, and we get that as we did last time. Now, then from the learned rules, we have to rattle them off in D, R, T order. So I can't see any D's, any dilations there, can you? No. So we've got an R, we've got a reflection. This is a reflection about the x-axis, and we've got 2 translations. This one, that means you've got to go backwards with this technique. So that means you've got 4 units down, 5 units to the right. That's right, yeah? See, isn't it confusing when you're trying to mix up the logical method with the Dr. T method? You know, you just have to be really careful. That's why you've got to do so much practice to get it right. So, I don't really think you should mix them up. I think you just should stick to one or the other, unless you're very good at it, you know? Otherwise, you just you end up in the algebra ditch. So, this gives us the information you needed to sketch the graph as we did before. Now we have to sketch this graph here. That's same old, same old. We use the base model as our reference point, and we use this one as that's the one that we're trying to sketch. So you put them in equivalent form, and oh boy, I forgot to push the stop buttons in this. Too much information. So that's equivalent form. I subtracted 1 from both sides and divided by 2, and I got that now. Okay, I can. Yes, so from the learned rules, we've got that's equivalent form. So, alright, we've got to do D, then R, then T. So D, there's a D there. That's a dilation of a factor of 2 from the X. Have we got any reflections? No. Have we got translations? Yes. There's 1 unit up and 3 units to the right. So let's see if that's what I got. Yes, I got that. Yes, I got that. Yes, I got that. Jolly good show, everybody. Now, with this information, we can sketch the graph as we did previously. Now, this is the one I want to show you. This is the one I want to show you. This is where Dr. T comes horribly unstuck unless you're extremely careful. We're going from the complicated version and transforming it to the base model. And guess what the one is that they give you in the exams? Exactly this one. And boy, does it absolutely cause an algebraic bloodbath. It does. So let's be careful, and I'll show you how I've managed to do this. So I don't like this method at all, but this is what you have to do with Dr. T if you're faced with this situation. So this is an example, yes, as I've written there, as we're moving from the transformed function, and then we're transforming it into the original function, if you like what I mean, to the base model. Yes, so yes, it gets very confusing. So what we can do is this is what I decided was the only way I could figure out how to do this. I decided to basically go from y equals 1 over x into that one as the transformed function. Right, that's my strategy. And then what I was going to do was so that's not what we're asked to do. That's not what we're asked to do. So I decided to go from here to there, which is not what we're asked to do. We're asked to go from there to there. But I can only use Dr. T going from the base model to the more complicated one. So I decided to go from the base model to the more complicated one, work out my sequence of transformations, and then quote them in exactly reverse sequence of the transformations in reverse order. That's all I could do as a way of reversing. I went from there to there, and then basically to reverse the sequence I had to quote everything in reverse, which would mean I'm going from there to there, if you know what I mean. Now, you know, if you want to do that, well, jolly good luck to you, but I don't like doing it. But I'm doing it here to show you. So if we let that actual one as be the base model, the original, which of course it's not supposed to be, and then we let that thing there equal where we're going, which it's not supposed to be. It's supposed to be the beginning one, but you know what I mean. So now I'm going to basically work up a sequence of transformations to get from there to there. Then I'm going to quote them in reverse order. So therefore, to get from 1 to 2, we have to... Am I in equivalent form? Oh, yes I am. Yes I am. Yes I am. I've already taken care of that, so good. Now I'm going to equate equivalent terms. So to get from 1 to 2, we therefore need, now, okay, dilation factor of 2 from the x-axis. There's a reflection about the x-axis, and there's 2 translations. There's a translation of 5 units. Now that's up. Remember, this is Dr. T. It's confusing. And 3 units to the left. That's right, that's right. Yes, yes, that's right. Now that gets me the sequence of transformations to go exactly the wrong way compared to what I'm supposed to do. But now I'm going to reverse everything, right? I'm going to reverse everything. So for the reverse scenario, we need translation of 3 units. I'm picking them off. I'm going in reverse order from this one backwards, right? So I'm saying 3 units to the right, but that's the first one I have to quote. Then I have to go 5 units down. I'm going reverse order, right? Reverse thingies in reverse order. And then I'm going to reflection about the x-axis is all right. That's still the same. Dilation of a factor of 2. Oh no, it's dilation of a factor of half. That's the reverse of a dilation of a factor of 2, is a dilation of a factor of half. So the only one that actually stays the same, it was the reflection about the x-axis, because you can't really reverse that, can you? It's just a negative, it's just a reverse way reflection about the x-axis, isn't it? You know, instead of reflecting, say, from right to left, it's reflecting from left to right, if you know what I mean. Right, so yeah, that's what you have to do if you're using Dr. T to go from the complicated to the base model. And I'm telling you, I'm not very impressed with that. So that's the end of the video. But if you like it, look, you do it. If you get good at it, you do it. You know, I'm not saying don't do it. I'm just saying be jolly careful. Alright, I'll see you next time. Have a wonderful day and see you. Bye bye.